Greetings and welcome back. I'm excited here to talk about, I think, one of the most fun topics there is in this whole course. And, for me, it's kind of been a lifelong quest, which is to try to understand the spontaneous direction of natural processes, to understand the time evolution of systems, to understand the things that I see when I look out my window, which is that the world is dynamic, it's changing all the time. And that for me poses a dichotomy because to me one of the most beautiful parts of all of science surely is the theory of equilibrium statistical mechanics. I've made a lot of noise about the work of Gibbs, and I'm a huge fan. I just think that that's so beautiful and so powerful. And so, I come to this topic with a real love and appreciation for out of equilibrium. But then my hackles get up because I feel that people have this reaction to the use of equilibrium, especially in biology, which is frankly pretty shallow. It's kind of a knee-jerk reaction. So let me strike my balance. So on the one hand, I deeply appreciate this article, which I recommend to you. It's called Nonlinear Science from Paradigms to Practicalities by David Campbell, who, if I remember correctly, is at Los Alamos National Laboratory. And that was where, in at least part of the time, the famous Polish mathematician Stan Ulam was present. And this was a very, very clever man, meaning Ulam. And I like this quote from Ulam. Stan once remarked that this was like defining the bulk of zoology by calling it the study of non-elephant animals, meaning, talking strictly about talking about non-linear phenomena seemed to get it wrong because it gave place of precedence to linearity, whereas in fact most things are non-linear. And non-equilibrium also has that same feel, and Julien Dallaire has remarked, saying non-equilibrium physics is like saying non-elephant biology. So I buy that. And I feel like, one of the greatest blemishes on modern physics, and it's an inheritance of modern biology, is the failure of physics to be truly on top of non-equilibrium. So again, that's all by way of saying I'm on board. I really, really want, like, the number one thing that I've wanted to know in my career, if I were to go to sleep like Rip Van Winkle for 100 years, if I were to awaken in 100 years, besides wanting to know whether humankind was still around, I would want to know whether we had come to some sort of more general terms with the idea of non-equilibrium. So again, I'm on board with that. But for the purposes of this discussion, I am absolutely not on board. And what I mean by that is that this does not give us the right to reject out of hand the use of equilibrium thinking in biology. And I'm going to try and make an argument. It's a semi-quantitative sort of street fighting order of magnitude description of separation of timescales. And one of my favorite things to show is a picture of lead pipes in London that are more than 50 years old. And what you'll notice is that they're sagging. They actually they've deformed under their own weight, and they're curved now. They used to be straight when they came from the factory, but now they're curved. And the reason for that is separation of timescales. On short timescales, clearly the pipe is in mechanical equilibrium. It's sitting there. There's some bolts holding it up. It's on the wall, and gravity's pushing it down, and sum of all the forces is zero. But if you want to go look out in the world of material science, there's a subject called creep, and creep refers to mass transport induced deformation, and over long time scales, a lead pipe will creep, and that means it will suffer permanent deformation. And that's a separation of timescales. So what I wanted to say is that, although I'm not going to spend a lot of time going into it, I just want to, for everybody's purposes, I want to make sure we're all clear on the following sort of harsh, huge assumptions that are made out in the world of science that one could have a knee-jerk reaction and reject them, but we would be the ones who would be naive. For example, when we first learn solid state physics, the first thing we learn about a metal is the so-called free electron gas picture. And there's really great things to learn about that. For example, there's a book by David Pines called Elementary Excitations in Solids. that has a really cool treatment of that. Chapter 1 of Federer and Walechka's book on quantum mini-body theory, I forgot the title of the book, has a beautiful treatment of the electron gas and how you can use it to get the energy scale, the bulk modulus, lattice parameter, of metals like lithium and sodium and potassium and rubidium and so on. These are first column or something. And so here it is. Consider a metal as a gas of non-interacting electrons. I mean, give me a break. You want to be upset about using equilibrium in biology? That's just child's play compared to the idea of imagining the Coulomb interaction as being irrelevant to a gas of electrons. If you calculate the ratio of the gravitational to the electrostatic force between two electrons, it's some crazy thing like 10 to the minus 42 or something. I did it a few weeks ago, but I forgot. I can't remember if I did proton and electron or electron and proton or electron and positron or whatever, but it doesn't matter. It's 39 orders of magnitude or something, 40 orders of magnitude. So electrostatic energies are huge, and yet, we make this assumption, consider a gas of non-interacting electrons. And so, an equally stark and bizarre idea is, I just want to tell you that, in the center of a nuclear explosion or in a star, we use equilibrium ideas. So, if you go, there's a really nice book on the history of cosmology by this guy, Longair, who also wrote a really nice book, Theoretical Concepts in Physics. And he has a cool description of the early days of trying to understand stellar atmospheres and the relative intensities of spectral lines, and in particular, trying to use our understanding of statistical physics to figure out the temperature of stars. I mean, imagine that. You're trying to figure out by looking at the spectral character of a star what its temperature is. How beautiful, how brilliant. So Saha wrote this equation, which is, tells me basically the degree of ionization, what fraction of the atoms will be ionized. And this equation, you can already see it just by looking at it, that it features an exponential of an energy over kBt. This is exactly what should conjure up for you images of the Boltzmann distribution and equilibrium statistical mechanics. And, it even says it here. I'm just quoting you right out of the wiki page. The Saha equation describes the degree of ionization for any gas in thermal equilibrium as a function of the temperature, density, and ionization energies of the atoms. And you can see here, is used to explain the spectral classification of stars. So, have people been more sophisticated? Do they think about dynamics? Yeah, sure. They have been and they are. But, this is exactly where you would imagine starting, and I love the idea of this equation serving as a stellar thermometer. Isn't that cool? Very beautiful. Okay, so that's my background. My background is just a bit of a rant to say that, at least for me, I feel cautious about rejecting things out of hand because I worry about the fact, I always think back to the electron theory of metals. It's just like, whoa, I need to be careful here because somebody actually made a lot of progress with the idea of consider a metal as a gas of electrons. That's really fascinating. So let me now try to walk you through an argument as to why I think it was great and interesting for us to define a free energy which depended upon the number of ions and the number of sugars on both sides. You'll recall, when we did the symporter, we studied it by writing down 4 objects. We wrote down the chemical potentials of ions on the outside, sugars on the outside, ions on the inside, sugars on the inside. That was 4 quantities, 4 chemical potentials, 4 derivatives of free energy with respect to particle number. And then we said that free energy itself measured the degree of this equilibrium and served as a driving force towards equilibrium. And we wrote down a relaxation dynamics of the form dN by dt is equal to minus some kinetic coefficient and then dF by dN. And this is the free energy. So we are explicitly, straightforwardly, openly embracing the idea of using the free energy even though we're not in equilibrium in order to compute the driving force that gives us the dynamics and the relaxation towards equilibrium. So that was our thinking. And what I want to do is I want to try to make an argument about this figure, which the students in the class did this as a homework. So what we're plotting here is the entropy in the left region over here, the entropy in the right region over there, and then the total entropy, which is the entropy summed up by adding together the entropy of both pieces. That's this green curve. And what we're doing is we're doing it as a function of the tuning parameter, which is number of particles on the left side. So we start out with 0 particles on the left side over here, so that would be this situation, basically. And it looks like maybe there's a mistake in the diagram or something. At any rate, so, as we tune the number of particles on the left side, then the entropy changes. And the only state of equilibrium is here, which is this, this diagram. When there's, for this particular geometry, when there's half and half on both sides. So how are we going to reason out why we might have gotten away with this idea of thinking of this as a series, as being defined by a free energy as the drive? So let me walk you through that. So here's the way I thought about it. So what I tried to figure out is what's the time scale for a molecule to transition between two lattice sites. In other words, if I focus on this particular guy and I ask the question, what's the frequency or what's the rate at which it moves to the adjacent box? How might I estimate that? Well, the answer is I will take the typical speed of a molecule in solution, the distance traveled, these boxes, they have a dimension d of order 1 nanometer. So I'm thinking of each one of these boxes as 1 nanometer cubed. And so that means the time to cross from one lattice site to the next is given by the size of the lattice divided by the velocity. So that's 10 to the minus 9 meters, and then divided by, I called it a few times 100 meters per second. So, the range of molecular speeds could be 100 to 600 meters per second. So what this means is that the time scale to go between two adjacent lattice sites is around 10 to the minus 12 seconds, a picosecond. And that means there are 10 to the 12th such transitions every second. Now, I could be done right now because I can tell you that if I think about, for example, the symporter Lac-Y, it makes 100 transitions per second. So what do I learn from that? What I learned from that is that there are 10 to the 10th molecular jiggles for every sugar before one of them makes a cross through the symporter. And that's the separation of timescales. It means that there has been time, if you like, for the sugars to thermalize. There is a separation of timescales in the sense that the sugar molecules in solution are establishing themselves as being in equilibrium in much the same way that, if you think about an ion channel is open for, milliseconds, but the transition time is of the order of microseconds. And so it's staying in a given state for quite a while, and then it makes essentially an instantaneous transition, and then it stays in the closed state for a while, and then it goes back. And so, on the time scale of the transitions, the time scale of resting in the open or closed state is basically really long. Another way to think about this that I just tried out was I said, well, let me, as an alternative, think about an ion channel where the channel is just open, and I want to figure out what's the number of ions or the waiting time between ions crossing the channel. So the number per time is given by the flux times the area of the channel. The flux is given by Fick's law, d delta c delta x, and then the area is delta y delta z. So I considered a jump in concentration of like 100 millimolar. You'll remember the rule of thumb that 1 per micron cubed is nanomolar, and so 100 millimolar is 10 to the 8th per micron cubed. The distance over which this occurs is about 10 nanometers. That's the jump distance, let's say. And so that gives me delta C delta x of order 10 to the 11th per microns to the fourth power. So I can now find the number per time. The diffusion coefficient is 100 microns squared per second. Delta C delta x is 10 to the 11th per micron to the fourth power. And then the area of the, one sec, I'm recording something. I'll be out in a few minutes. Oh, okay. I'm gonna be back in a second. Sorry, you'll just have to sit there. All right, I'm coming back. Sorry, I don't know. This is life in the pandemic. Somebody was at the door. It was something that was urgent, had to be taken care of now. Anyway, so what was I saying? I was saying, we're basically using Fick's law, and the area of an ion channel, I don't know, like 10, it doesn't really, this is completely irrelevant, but, I'm trying to point out that even in this case, we get about 10 to the 7th transitions per second. But I said that the jiggling time is 10 to the minus 12 seconds. So, the waiting time, the amount of jiggling time that I take up between steps is like 10 to the 5th hops. And to put this in perspective, I guess I was amused by this. If I think of a human lifetime, let me be sloppy and say 100 years, then 10 to the 5th such lifetimes gives us 10 million years. So that's saying that, from the perspective of the jiggling sugar molecule, it'd be like for me to wait a time equivalent to the time since we had our most recent common ancestor with the chimps. I hope you're getting a sense of what I'm trying to convey here. It's like these time scales are all very fast for our everyday experience, but they are hugely different from each other. And I'm trying to make the argument that this licenses us often, not always, but often, to get away with equilibrium thinking. But it's I shouldn't even say getting away with it. It's quite justified, I think, is the way that I might want to think about it. So I wanted to use the language of the mean free path as an alternative way for us to think about this. So the way I want you to imagine this is that that there's a certain density of sugar molecules, which I'm showing here in yellow, and I want to find out how often do they collide with each other. And the reason I'm interested in that is I'm thinking of the collisions as thermalizing the sugar molecules, which again has to do with, how do I ensure that I can get away with treating them as though they're in equilibrium instantaneously. And so the idea here is that the density of molecules is given by there's one molecule in a cylindrical tube, which I draw here, whose length is equal to v times the collision time, and whose diameter is basically 2 times the diameter of one of the molecules. In other words, if the two of them are traveling like this, and they're within a diameter of each other, they're going to hit each other. And so what we're doing with this mean free path idea is we're basically setting up the question. It's a little naive the way I'm doing it. There's square roots of 2's that come out if you do it more exactly. Not relevant for what I'm trying to say today. So the density of molecules is 1 divided by the cross-sectional area, which is pi d squared, and then times the length, which is v delta t. So I can solve this for the collision time, which I do here, and then I use the density is 1/10 per nanometer cubed. That's 10 to the 8th per micron cubed. It's the same thing. A micron cubed is the same as 10 to the 9th nanometers cubed. So you can see here's my density. So 1/10 per nanometer cubed. The size I took, few is pi, and then 1 nanometer squared I just took as the cross-sectional area, and then the velocity I took a few hundred meters per second. That gives me a collision time of 10 to the minus 11th seconds. So that means, again, that when I wait until I get a symporter event, I'm going to wait 10 to the 10. I'm going to have 10 to the 9th collisions of my sugar molecule of interest before it transits across the symporter. And so the argument is that there has been sufficient time for thermalization. Okay, so that's my little attempt at using street fighting to at least make the argument about why separation of timescales is actually a thing. It's not a fantasy. And there are lots of times when one can make a rigorous argument and get rid of things and simplify. And although people often have this tendency to think of that as naivete, to me it's really exactly the opposite. It's the height of sophistication. And this is I think, a very beautiful example, which is separation of timescales.